G'day, and welcome to my talk, Why Teach the Why? We're going to talk about how context empowers learning and about how carving out time to dedicate to context improves outcomes and can reduce the time that you have to spend on revision. Let's start with who I am and why I'm giving this talk. I'm Jack. You probably got that already. I'm the CTO and co-founder of Kumo Study. We make study management tools for learners with ADHD and tools for institutions to support them. And I'm a computer science educator. I have a decade of experience teaching at camps and workshops and incursions, as well as I spent 2 years teaching at a high school in Sydney. I want to kick things off with a little scenario that I think all of the educators in the room here have probably experienced. Don't worry too much about the specifics, it's more just the general shape of the scenario. So you spend some time teaching, say, databases or some other topic to your students, and it seems like they understand it, and it's all going pretty well. And then you move on to another topic, say, cybersecurity or electronics. Again, they're understanding it, and things are going well, and then a student asks how they're related. Or for another example, suppose you're teaching a topic that necessitates a bit less time, maybe image file formats or different storage technologies, and you cover what's discussed in the curriculum, and then you move on to the next topic. And then come time for the assignment or the exam, it seems like the students have more or less forgotten everything about that topic. These scenarios highlight the only problem with the curriculum. And it's one shared by basically every computer science or technology curriculum I've seen. There's too much stuff in it. When a curriculum has a variety of topics, it's very easy to fall into the pattern of racing through them. Of course, you try and put them in a sensible, cohesive order, but there is only so much that can be done. This leads to students feeling like the course is a mishmash of different elements, unrelated to each other. And this in turn leads to students having a hard time building a strong mental model of the course, and so more time has to be spent on revision, further cutting into time to cover the curriculum. So, what can you do about it? Well, context is critical. I have found that when I spent more time on context, I was able to mitigate those problems to quite a considerable degree. I actually spent very little time on revision, only a handful of weeks across all of years 9 and 10. And even then, with very little prompting, the students themselves actually provided the solutions for the initial examples I worked through on the board before I handed out revision sheets or cheat sheets or went through it again with them. But most importantly, I found that students grew more engaged and excited by our classes. They were very motivated to join in on class discussions, they always wanted to know more, and they became excellent at connecting disparate topics together. So let's clear up what I mean by context here. Since it's a bit of an ambiguous word, it could really mean almost anything you want it to mean. What I mean, at its core, is why is this the way that it is? The answers to this question vary wildly depending on the topic at hand. There's historical and social reasons, there's limitations of technology, of when the topic was developed, and sometimes there's just the plain physics of the universe. I always ask myself, and I encourage my students to ask, why did the people making this technology, system, standard, or whatever, do it this way? People, by and large, don't do things for no reason. They may have a bad reason, but even a bad reason helps you understand. For example, you've most likely heard the opening line to A Tale of Two Cities by Charles Dickens. It was the best of times, it was the worst of times. But Dickens goes on. It was the age of wisdom, it was the age of foolishness. He continues further. It was the epoch of belief, it was the epoch of incredulity. Light and darkness, hope, despair. On and on he goes. He's supposed to be this great writer, and certainly best of times, worst of times is a banger of a line. But why does he just keep going, driving his point into the ground? We get it. Things were both one way and the other way at the same time. London is two cities at once. Why are you like this? Well, Dickens was paid by the word. And suddenly all of that makes sense, doesn't it? And odds are much slimmer that you'll forget either that he was paid by the word or that there is much more after that famous line. So, how did I do this in class? For our first example, we'd already done a term on programming. They were pretty comfortable with Python, including using multiple conditions in an if statement. And we'd moved on to logic gates and Boolean algebra. So, multiple conditions in an if statement. And they were getting it, but not as quickly or as well. And I realized that the problem was that all the exercises, even when wrapped up in a scenario or a story, just kind of look like this. And it's just shapes on a page. They're not shapes you really see out in the world for most people. Certainly they weren't seeing them outside this classroom. So did this stuff even matter at all? I mean, sure, I knew that it did. But how do I convince them? So I started by taking a step back and asking myself, okay, well, what is this used for? And it's used for designing circuitry. So what does that circuitry build? Well, computers, of course. So I decided it was time to stop doing abstract problems and start building a computer from scratch. As a reminder, these kids are in grade 9. So we start out with the simplest thing that I could think of that could be called a computer, a 1-bit adder. It takes in two 1-bit numbers, and it adds them together, making a new 2-bit number. So working together, I explained what we were doing, and together on the board, we drew up a truth table for the 1-bit adder. And I told them to design a logic circuit that replicated this truth table. And they all made things that looked roughly like this. Once they did that, I congratulated them on having built a computer from scratch. It seems silly, but they genuinely had. This wasn't an abstract puzzle. This wasn't just plugging numbers into a formula. They had, on their own, designed tiny computers. So, naturally, I escalated. I then said, okay, we're going to make a 2-bit adder. Now, we can't quite just copy what we did, because we've got that carry bit coming in from the 1-bit adder. So we had to make a new truth table that accounted for that, and then design a new circuit. And so we made a 1-bit full adder. And once we had that, then we just had to glue 2 of them together, like so. And then you can glue 2 of those together, and 2 of those together. And now you've got a 1-byte adder. So now we're really cooking with gas. We've designed a computer that can take any 2 numbers between 0 and 255 and add them together. And that's pretty cool for a bunch of grade 9 kids to have done. I also brought in some old logic gate chips that I have to show them that these things, these gates, physically exist. And if they wanted, they could go and buy some buttons and wires and more gates, and they could build the design that they had just made, and it would work. I think actually doing that in class would have been a great thing to do, but unfortunately I didn't quite get around to it. Next time, hopefully. By the end, and then we continued on. We kept expanding this computer, adding more features and functionality to it. By the end, it could add and subtract bytes using 2's complement. You could put the result into one of either 2 bytes in memory, and it could be given an instruction consisting of 2 bytes of data, whether to add or subtract them, and which memory address to store the result in. So this is genuinely a computer, with no hint of exaggeration. I showed them how you can take the binary for that input there, and that's called an opcode. And this is the basis of machine language. That's what assembly languages directly translate into. It's what Python indirectly becomes. All told, we spent most of term 2 in grade 9 working on these computer designs. And then, after their assignment was done, we did not touch logic gates again until term 3 of year 10. So over a year later. And guess what? They remembered it pretty well. They weren't entirely certain of which symbols were which gates, but they were largely correct on that, and they knew how to make a truth table and make a circuit, and they knew how to take a circuit and make the truth table from that. They knew how to actually use the logic gates in a way that I only ever learned in university. This also works with smaller topics. So I was teaching the Cambridge IGCSE curriculum, and according to it, there's only one thing you need to know about sound files. So you're getting the inside scoop on what that whole curriculum covers there. Sound files have a sample rate, and a higher sample rate means a higher quality sound file. Congratulations, you've graduated. So that's just one sentence, and you can probably memorize it pretty easily. But rote memorization, I feel, isn't a satisfying learning experience. It's not going to enthuse the students, and it's prone to being forgotten. So I asked, okay, what is the sample rate, and why does it make a higher quality sound? And before I could answer that, I had to ask, what even is a sound? I forgot to click through my slides. Sound is the vibration of particles in air, and we can represent that vibration with waves. A simple sound of just a single note is a nice sine wave. But these waves can be combined to show more complex sounds like chords and human voices. In order to reproduce these sounds, speakers vibrate in and out, controlled by an electromagnet, to push the air in the same pattern. And so this complex wave, or even a simple wave in fact, effectively shows the position of the speaker at any moment in time. And the sample rate is how often we check where the speaker should be. If we go back to the simple example, we've got just a single note here at 500 hertz. This graph just shows an 8 millisecond slice of it. At one extreme of sampling, we have the perfect sample. This is if we could somehow sample every infinitesimal slice of this graph, and then we can reproduce the sound perfectly. But then if we're going to store this digitally, then that requires infinite digital storage space, and I don't have that. So let's jump to the other extreme and go for a very low sample rate. You can see our original signal in blue here, and if we sample the note at the same frequency, 500 times a second, we get that red line here. So it's always at 0, and the speaker doesn't move. So that's not going to be enough. If we go just a little bit more frequently, say 502 times a second, we can see that we've got a sample that slowly moves the speaker. This is clearer to see what it's doing wrong if we expand this view out to a whole second of the sound wave. We've got our original sound wave at 500 hertz still in blue, and we've got what comes out of our sample here, and that's definitely not the same note as the blue wave. That's only about 2 hertz. So let's go to something more reasonable. Something that would be low quality but actually produce a sound. Let's sample 2,000 times a second. Now we're seeing some samples that start to actually make sense. We get this triangular wave pattern, so it will still sound weird and robotic, but at least it is the right pitch now. It will also struggle with a more complex sound wave. You can see that much of this wave gets cut off, and so the sound is going to be heavily distorted. So we need the sample rate to be at least 4 times the frequency of the highest sound that we want to record. Human hearing range is generally between about 15 to 20 kilohertz, but the top end of that isn't commonly used in audio files or music. The highest note on a piano is just under 8 kilohertz. So we'd need a sample rate of at least 32 kilohertz. We can go higher for smoother, more natural sounds, as well as to accommodate the top ends of the hearing range. So audio is commonly recorded at 44.1 kilohertz or 48 kilohertz. This graph shows here an 8 kilohertz sound recorded at 44.1, and you can see that it's not perfect. You do get little clipped edges on a lot of the waves, but overall it's a pretty close match. Now, in class, I actually went through all of these graphs with my students. We saw what the sample rate was, we saw how it impacted the quality of an audio file, and we really understood the maths behind it. We covered this over a single lesson. It didn't take much longer than I just spent with you. And we covered this in the first few weeks of grade 10, and then we didn't discuss it for the rest of the year. All of them got this question right on their final exam, though. I didn't discuss it again since then. We didn't revise it. Nobody asked me about it. They all got it right. So, those were some pretty long examples, but I wanted to emphasize the kind of approach that I take in these discussions, really exploring the space and uncovering that context. But how do I achieve this? Am I just some kind of super genius who knows everything? Nah, I use Wikipedia loads. I don't want to be too flippant here, but I cannot overstate how good Wikipedia is. Let's take a look at the Wikipedia page for audio file format. It's got a bunch of stuff here that seems well out of my depth, but if we scroll down or if we search the page, hey, it says sample rate. And I knew from the line in the textbook that that was the thing that we cared about. So let's click that and go to that page. And we're going to check out this article. And it goes into more detail than I did, but it covers a bunch of the same stuff. You can see there that graph, not too dissimilar from the kind of graphs that I was drawing. So with just 2 pages on Wikipedia, we can get a decent idea of what a sample rate is, and then convey that explanation to our students. This is true for pretty much every technical topic. I think largely because Wikipedia has come up in the age of computers, fairly obviously. It has a lot of stuff about computers and about computer science and everything on it. So if you are teaching computer science at all, it is an excellent source to learn about the context and the history and the why things were done the way they were. The other 2 big tips are, firstly, that you don't need to know it all. You just need to know enough to make it real. A few little tidbits to tie it to the context is entirely sufficient. All that matters is that there is enough there for them to latch onto and go, this is something that impacts the real world, this is something that a real human being put thought into, maybe not a lot, but they put some thought into it, and they made it, and there were reasons behind what they did. The other big one, involve your students. You can give them research tasks, or have an open discussion. I found asking, why do you think they made it like that, is a great way to get a discussion going. Oh no, I pressed a button because I dropped the thing. Why do you think they made it like that? That is a good question. Why is there a button right under where your thumb sits that exits the whole presentation? Yes, maybe not a good reason. So, an excellent example I had of this was, I found that this worked particularly well for topics that are maybe a little controversial, you've got to pick the right ones, but a little controversial or current, or there's a lot of ambiguity floating around. We had a great discussion in class about NFTs. I explained what they were, how they worked. I explained blockchain, how that worked, and I asked them, why do you think NFTs work like this? And there was a pause, and one of them said, it just seems like gambling. And I said, okay, go on. And she said, well, it just seems like the only way that NFTs make money is if somebody buys the one that you bought for more than you bought it, so you're just hoping that somebody will. So it's just gambling, right? I'm like, you're entirely correct. The whole thing is a scam. Maybe don't buy NFTs. She later told me that her dad had been planning to buy NFTs, and she told him, and then he did not. So, success. There are some caveats I do want to address here. Got applause from the other room, too. Firstly, I had a rare environment that I understand that I was privileged to be in. I had small classes, at most a dozen, at a private girls' school. And while none of these girls had prior digital technologies experience when they entered my class for the first time, they were girls who were expected to do well academically by their parents and by the school. I was also teaching the Cambridge curriculum, and it is designed around the students getting more time per subject throughout the school year. The school that I was at spread this time out over 2 years, but it probably only needed 1.5 years. This afforded me some time to experiment with this approach that I knew that I could make up at the end if I needed to do just as much revision as I had initially thought. Luckily, I have done some of this experimentation for you, and so you can try this out with a little more confidence that it will work, hopefully. I also studied computer science at university. I am a software developer by trade and have spent many years as a professional developer before I taught at a school, and so I have had plenty of time to familiarize myself with a lot of this context before I got into the classroom. So I had to do less of that Wikipedia research now, and I did that at university. Lastly, I have wicked ADHD, and I absolutely live for going down a rabbit hole and learning how a thing works. Digging into the history or the politics or the physics behind something is when and where I thrive. I am told this is not for everyone. I want to focus that while I want to emphasize that while focusing on the context worked for me, I understand it might not work for you. Still, I would encourage you to consider it and give it a try. I certainly saw results with it, and not just because I'm a big softie and gave everyone great marks, even if they didn't deserve them. These students did the Cambridge exam, which is run and assessed independently by people from Cambridge. So I have some external validation here. I only had a single cohort that I taught in the South for the whole 2 years of the course, so unfortunately my sample size is low. But of the seven students who did that exam, 5 of them scored an A star, which is Cambridge's highest grade, and 1 scored an A. These are girls who had never had a computer science lesson before our classes. They'd never programmed, they didn't know any electronics or logic gates or databases. Cambridge grades on a curve, so to get an A, you need to get 88 or above out of 150. These girls scored an average of 112.8. My supervisor said that the school had never achieved results like this before in computer science. It is not a silver bullet, however, and if a student is disengaged, no amount of context can fix that. You might have noticed I said I had 7 students and then I gave you 6 grades. The last one, unfortunately, did not do as well and got an E. There is only so much that you can engage somebody who does not wish to be engaged. So, all in all, I'd encourage you to try it. I would love to hear how you go with it. Thanks for coming to my talk.